Hello, welcome to More Learn, More Teach, where I attempt to simplify the complex. All right, so now that we know how to add and subtract vectors, let's look at an application. So if I have vector A, I can say that vector A is made up of two added vectors. I can have a vector coming this way and add a vector going this way to make up this vector. So I can have an x component if I define this direction as the x direction, and a y component if I define this direction as the y component. So if I add this component vector A to this component vector A, I get my whole vector A that I started with. Okay, so I could say that the vector A is equal to the vector of A on the x direction plus the vector of A on the y direction. So if we look back, quick review of trigonometry. If I have a right triangle, the hypotenuse is the longest side. I have some defined angle. I have an opposite and an adjacent side. If I have that, then the sine of the angle is equal to the ratio of the size of the opposite side divided by the size of the hypotenuse. The cosine is defined as the size of the adjacent side divided by the size of the hypotenuse. I can use the Pythagorean theorem to say that a squared plus b squared equals c squared. So therefore, the adjacent side squared plus the opposite side squared is equal to the hypotenuse squared. Substituting in, I have the hypotenuse times the cosine squared plus the hypotenuse times the sine squared is equal to the hypotenuse squared. Now the hypotenuse squared will divide through, and I have that the cosine squared plus the sine squared is equal to 1. All right, so back to this. If I have some vector A, so some vector A, I can find the component of the opposite side by multiplying the sine of this angle by the magnitude of this hypotenuse, the magnitude of the vector. So therefore, the y component, if I define the opposite side as the y side, the magnitude of this y component is equal to the magnitude of the hypotenuse, or the magnitude of the vector, multiplied by the sine of this angle between the vector and the x-axis. The x side is the cosine relationship. So if I want the component of the x side, or the projection of the vector on the x-axis, or the shadow of the vector on the x-axis, I have the magnitude of the x component is equal to the magnitude of the vector multiplied by the cosine of the angle. Now that we know a little bit about component vectors, let's talk about something called a dot product. So let's say that I have two vectors. I have vector A and I have vector B. Vector A has two component vectors, one along the x-axis, one along the y-axis. So I have the x component of A and the y component of A. And I have B, which has a B in the x component, so the x component of B, and B in the y component of B. So a definition of a dot product is one vector dot another vector. This is also called the inner product. The inner product vector, it's a scalar product of two vectors. This is equal to the summation from k equal 1 to n, where n is the number of orthogonal directions, of the magnitude of the k component multiplied by the magnitude of the b component. So if I look in my two-dimensional space, right, I have my two-dimensional space here where I have an x and a y. A dot b, by definition, will equal to the magnitude of A in the x direction multiplied by the magnitude of B in the x direction. That quantity plus the magnitude of A in the y direction multiplied by the magnitude of B in the y direction. Okay? So using our trigonometric rules, we know that the magnitude of A in the x direction is given by the cosine of the angle, right? The cosine of the angle. So A, magnitude of A multiplied by the cosine of the angle A would be along the x-axis, gives me the magnitude of the x component of A. The same thing for B. That gives me this x component. For the y's, y is going to give me the sine, right? So it's the opposite side. So I use the sine in order to get the magnitude of these vectors on the y component. So this is what I end up with, is magnitude of A cosine of angle A multiplied by magnitude of B cosine of the angle of B, magnitude A sine A, magnitude B sine B. Okay, so now I'm just going to do some algebraic manipulation. Rearranging my formula, I have the magnitude of A times the magnitude of B times all of the cosine and sine terms grouped together. I'm doing this because I want to use my trigonometric identities. So if I have two different angles, I multiply the cosines of those two angles, I have the cosine of these angles subtracted plus the cosine of these angles added, all divided by 2. If I take the sine of the angles, multiply those sines together, I have, again, cosine of the difference angle minus cosine of the added angle, all of that divided by 2. This is the trigonometric identities. So if I use these trigonometric identities and just plug them in, all I've done is taken cosine A, cosine B, and transform that into cosine of the difference angle plus the cosine of the added angle, all divided by 2. Taking this sine A times sine B, transform that into cosine of the difference angle minus the cosine of the added angle, all that divided by 2. So I've rewritten our expression. So I have A dot B is equal to the magnitude of A times the magnitude of B times our identity for the multiplication of the cosines plus my identity for the multiplication of the sines. Combining my like expressions, I can isolate my difference angles and my added angles, and I can see that these two will cancel out. These two are the same, so I end up with magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. So what this is telling me is that the dot product is related to the angle between the two vectors. As the cosine approaches 0, so if cosine of 0, i.e. I have the same angle, cosine of 0 is 1, I will have the maximum, which is A times B, right? So the magnitude of A times the magnitude of B. So the maximum dot product will be when the cosine term is 1, which is a difference angle of 0. So they are exactly overlapped. I get a minimum when the cosine is 0. Cosine is 0 when this is 90 degrees. So when I have the cosine of 90 degrees, are they exactly perpendicular, right? So if A is perpendicular to B, then this term becomes 0. Dot product of two perpendicular angles will be 0. You see that from this expression. So we can say that this is a measure of the projection of one vector on another. We could say that this is a measure of how much overlap you have between two vectors. And this will be very useful when trying to describe physical phenomena. So let's see an example of a dot product. So the work done by a force is equal to the vector of the force dot product with the vector of the displacement. So I have an example here of a block sliding down a frictionless plane. So the block has a weight of 1 Newton, and this inclined plane has an angle of 30 degrees. We want to know the work done traveling 1 meter down this inclined plane. So our force vector is straight down from the block. So straight down from the block, I have 1 Newton pulling from gravity on this block straight down. The displacement is going to be in this direction. However, I've got this angle here of 30 degrees. I need to get to where the displacement angle is. I chose to do it this way. There's many ways to do this problem. I wanted to illustrate some of these angles and some different ways, tools you could use to solve these kind of problems. So I've chosen to find the negative of the displacement first. So the negative displacement angle is going to be from this origin pointed up the inclined plane, and we'll have 30 degrees relative to this horizontal. So since I start with this 30 degrees, if I want to go to the same direction as the force vector, because remember what I'm trying to find ultimately is the angle between the force vector and the displacement vector. So if I'm trying to go relative to the vertical here, I can just add the 90 degrees difference between the horizontal and the vertical. If I add this 30 degrees to the 90 degrees, I end up with 120 degrees for this negative displacement vector relative to the force. So I don't want the negative displacement though, I want the positive displacement. So I'm going to add or subtract 180 degrees, which is exactly the same thing as taking the negative sign. So I'm going to go ahead and subtract my 180 degrees. So 120 minus 180 is equal to negative 60. Want to go ahead and illustrate this. Remember, cosine is an even function. So the cosine of the negative angle is the same as the cosine of the positive angle. Went ahead and kept the negative angle here in my equation just to make it simpler for you. However, you could have just used 60. It works just fine because the cosine function is an even function. So the work, which is a scalar energy value, is equal to the force vector dot product with the displacement vector. So the magnitude of the force, which is 1 Newton, the magnitude of the displacement, which is 1 meter, multiplied by the cosine of the angle between them. That angle between them is negative 60 degrees or positive 60 degrees, depending on whatever you want to put in your calculator. Really, if you just look at the references, right? So negative 60 degrees means we're going this way. Positive 60 degrees means we're going this way. Either way, you end up with cosine of 60 or cosine of negative 60, which is 1/2. So half of my force vector is not performing work on this system. So I end up with only 0.5 Newton meters of work done to travel 1 meter on this frictionless plane. Thank you for watching my video. Please like and subscribe. If you have any questions that I can help you out with, I'd be happy to try and answer your questions. Send me an email at morelearnmoreteach@gmail.com.